You know, Lewis structures are awesome for a quick sketch, for counting electrons, but let's be real, they're flat. They don't tell you why methane is a perfect tetrahedron or why beryllium fluoride stretches out in a perfectly straight line. To really understand the 3D shapes of molecules, the shapes that literally define how things work, we've got to go deeper. We need to take a leap into the quantum world of atomic orbitals.
So here's our game plan. We're going to start with a weird bonding puzzle that simpler theories just can't crack. Then we'll unveil the solution, this amazing idea called hybridization. We'll use it to build up the most common molecular shapes, then we'll tackle some more complex ones, and finally, I'm going to give you a straightforward toolkit to figure out the hybridization for pretty much any atom you'll come across.
All right, let's dive right into the problem. We've all used VSEPR theory, right? It's great for predicting shapes. You just imagine electrons are like balloons, pushing each other apart. But it's just a model. It doesn't really explain how the orbitals themselves, the actual homes of the electrons, rearrange to make those shapes happen.
To get to the how, we've got to start with something called Valence Bond Theory. And at its heart, it's actually super simple. It just says that for a bond to form, the orbitals from two different atoms have to physically overlap, kind of like a handshake. That shared space lets them share their electrons, and that's what holds the molecule together. Simple enough, right?
Well, that simple idea immediately runs into a huge problem. Let's take a look at beryllium fluoride, or BeF₂. We know this molecule exists. We can make it in a lab, and we know it has two identical bonds. But look at beryllium's electron configuration in its ground state. Both of its valence electrons are paired up in the 2s orbital. According to valence bond theory, it has 0 half-filled orbitals. It shouldn't be able to form any bonds at all. So what's going on? How does this thing even exist?
And this right here just lays it all out plain as day. On one side, you've got beryllium with its full 2s orbital, completely unavailable for bonding. On the other side, you have fluorine with a half-filled p orbital, just itching to make a bond. The pieces just don't fit. Our theories as they stand can't explain this at all.
And that brings us to the brilliant solution. To fix this gap between theory and reality, scientists came up with an incredible concept. Now, this is absolutely key, so listen up. This is not a physical thing an atom actually does. It's a mathematical model. It's a way of thinking that lets us perfectly predict the real-world shapes we see. And it's called hybridization.
So how does this thought experiment work? Well, it's kind of like a two-step process. First, we just imagine promoting one of those 2s electrons in beryllium up to an empty 2p orbital. Yeah, it costs a little energy, but hey, now we have two unpaired electrons ready to make two bonds. Then, for step 2, we mathematically mix that 1s orbital and that 1p orbital to create two brand new, totally identical hybrid orbitals.
So let's lock this definition in. Hybridization is a mathematical trick. We're not saying the atom is literally putting its orbitals in a blender. What we are saying is that if you combine the wave functions, the mathematical equations that describe the orbitals, you can create a brand new set of hybrid orbitals that perfectly explains the molecule's shape and bonding. It's a model that just works.
Okay, so this whole model isn't just a free-for-all. It's got some ground rules. First, you get out what you put in. If you mix 1s and 1p orbital, you get two hybrid orbitals out. The number is always conserved. Second, the shape and energy of these new orbitals totally depends on the original recipe. And third, and this is the most important one, the atom will always choose the hybridization that makes the molecule as stable as possible, the one with the lowest overall energy.
All right, enough theory. Let's actually put this stuff to work and see how it builds the shapes we know and love. We're going to start with the basics.
So let's go back to our problem child, beryllium fluoride. The solution to its puzzle is what we call sp hybridization. We take that 1,2s orbital and 1,2p orbital, we mix them together, and what do we get? Two brand new identical orbitals we call sp hybrids.
And this is where the magic happens. Since these two sp orbitals are identical, they want to get as far away from each other as possible. And how do they do that? They point in completely opposite directions, creating a perfect 180-degree angle. This gives us a linear geometry, which is exactly what experiments show for BeF₂. Boom, problem solved, the theory matches reality. Okay, so what happens when a central atom needs to form three bonds, like the boron in BeF₃? Well, the logic is exactly the same. We just add one more p orbital to our recipe. We mix one s orbital with two p orbitals, and we create three identical sp² hybrid orbitals.
And you guessed it, to get as far away from each other as they can, these three sp² orbitals spread out flat in a single plane, pointing to the corners of a perfect triangle. This creates what we call a trigonal planar geometry, with bond angles of exactly 120 degrees. And wouldn't you know it, that's precisely the shape of boron trifluoride. The model keeps working.
Okay, you see the pattern here, right? Let's take it up another notch. Think about carbon in methane, CH4. It needs to form 4 bonds. So what do? We mix its 1s orbital with all 3 of its p orbitals, and that gives us 4 new, identical sp³ hybrid orbitals.
So how do 4 things get as far apart as possible in 3-dimensional space? They point to the corners of a tetrahedron. This arrangement gives us that classic bond angle, 109.5 degrees. And since we made these from 1s and 3 p orbitals, we say they have 1/4 s character and 3/4 p character. This tetrahedral shape is literally the backbone of all of organic chemistry.
All right, so far so good. But what about the bigger molecules, where the central atom is bonded to 5 or even 6 other atoms? Well, for elements in the 3rd row of the periodic table or below, they have these empty d orbitals just sitting there, and we can pull those into the mix to expand the valence shell and make more bonds.
Believe it or not, the pattern just keeps going. If you have 5 electron domains, you mix 1 s, 3 p's, and 1 d orbital to get 5 sp³d hybrid orbitals, and they arrange themselves in a trigonal bipyramidal shape. If you need 6 domains, you just grab another d orbital, creating 6 sp³d² orbitals, which point to the corners of a perfect octahedron, just like in sulfur hexafluoride.
Okay, we've gone through all the heavy theory. We've built this model from the ground up. Now let's boil it all down to a super simple practical toolkit that you can actually use to figure this out quickly.
Okay, lean in, because this is the secret sauce. This is the big shortcut. You don't have to go through electron promotion and mixing every single time. The hybridization of that central atom is directly tied to the number of electron domains around it. All you have to do is count the things attached to it, the bonded atoms and the lone pairs, and that number tells you everything you need to know.
And this table right here, this is your cheat sheet, your master key. It connects everything. Step 1, draw the Lewis structure. Step 2, count the electron domains. Again, that's atoms plus lone pairs around the central atom. Step 3, just match that number to the chart. 2 domains, it's sp. 4 domains, sp3. 6 domains, sp³d². It's that simple. A direct link from the shape to the hybridization.
And through all of this math and all these models, let's not forget the why. A molecule isn't sitting there with a calculator trying to follow our rules. It's physics. It's just settling into the most stable, lowest energy configuration it possibly can. Hybridization is just the quantum mechanical language we developed to describe how its orbitals rearrange themselves to find that sweet spot of maximum stability.
So we've got a fantastic way to explain sigma bonds, those single bonds that make up the skeleton of every molecule. But think about it for a second. In sp or sp² hybridization, we had some p orbitals that we didn't use, right? They were just left over. So what are they doing? Well, it turns out they're the key to understanding double and triple bonds. But that's a story for another time.